Hello, everyone. This is Shauna, and in this video, I'm discussing the correction to an example that we did in class. I'm hoping that by going through it again, that it will make more sense to you and it will help correct some of the misunderstandings that I saw going on in class and maybe give us a chance to go over a few of the finer points for partial fraction decomposition that some of you might have missed. So let's take a look at it. For reference, we're going to be going over this example. Whoops, not here. We're going to be going over this example, but I'm going to go back to the beginning. We're going to be going over this example again, x squared plus x plus 3 over x cubed plus 2x dx. Okay. So this is the example where she made a mistake with the solving for the coefficients. We'll get to that in a minute. But let me bring up this share here. And let me expand it so that it's fully on screen. There we go. Okay, so anytime you have any kind of rational function, okay, probably the first thing you want to check for is whether you can make a u substitution right away. But I think it's fairly obvious that if I tried to make a u substitution, even for the bottom, the derivative here would be 3x squared plus 2, and we don't have a way to write that very easily in terms of this top part. So generally what happens is you're going to think about breaking this fraction, this rational function, into its constituent fractions, okay? But before you start to just blindly apply the cases that we saw in class, I want you to always check, is the degree of the numerator smaller than the degree of the denominator? Because this can get you in trouble. It got me in trouble on one of the problems that I was doing. This is x squared here. This is x cubed. So this degree is smaller. If the degree is smaller on top than it is below, you're fine and you don't do long division. But if the degree on top is larger, you have to do long division, and then you do partial fractions, but only on the quotient part of the answer, okay? So we don't have to bother with long division, but we have to resolve this into partial fractions. Now, some of you had a question about this. Linear factors, okay, so I factor the bottom, this x cubed plus 2x, I factor out the common factor of x, and I'm left with x times the quantity of x squared plus 2. A linear factor, when we talk about linear factor, that means that this x or this variable or this term is to the first power. I could have something in parenthesis like x plus 3 or x plus 2, and that would still be linear because the highest power on that is a 1. So this x is a linear factor, and linear factors take linear coefficients at the top. They don't have any x's, and they don't, so you just have a over x here, and a because this is the first coefficient. Now, this x squared plus 2, okay, we only have one factor of x squared plus 2. There's no square. If I had a square on this, for example, here, then I would have a repeated irreducible quadratic, but I don't, okay? I don't have that. So what I'm going to do is I'm just going to use, this is a quadratic and it's not reducible. I can't factor it anymore. So I'm going to end up with a linear factor on top, bx. Notice I have an x here. I have two coefficients, bx plus c, because I need to introduce that x term, and I need a constant factor after it, okay? Over x squared plus 2. That's where it came from. If any of these factors had been repeated, like if this x had been repeated, then I'd have a b over x for however many times it were repeated, x squared, x cubed, or whatever, okay? But that's the difference. Now, now for the good stuff, okay? Because we have a long way to go with this. So now I get to my coefficient. Now I need to find my coefficients. So what I'm going to do right here is this thing on the right side. I'm essentially, think of it as multiplying, if this helps you at all. You can think of multiplying the whole equation by this denominator, okay? Essentially, what we're doing is we're saying we're getting a common denominator on the right, and then we're equating the numerator on the left with the numerator on the right, because if I have common denominators, and I don't on the right now, but if I do have common denominators, then I can equate the top and the fractions will be equal, which is what we're doing. So if you think of multiplying this by multiplying by the denominator all the way across, you would end up with x squared plus x plus 3. This x would cancel with the x that you multiply by in the denominator. You get x squared plus 2. And we put it in parentheses because we're multiplying the whole term by it. And this bx plus c over x squared plus 2, the x squared plus 2 would cancel, and I would get bx plus c times x, which is what you see here. Now, all I did on the right was distribute. So a times x squared, ax squared, plus 2a, bx squared plus cx. Now, you don't have to do this next step. I put in an extra step here just to make this a little more readable. I don't do this all the time, but I did it here. So what I did was I just grouped these terms in descending order. Ax squared plus bx squared plus cx plus 2a, okay? And what we're doing is we're factoring out the common factor by the powers of the variable. So x squared times a plus b plus x times c plus 2a. Now, if you look closely here, you have a situation where let's see. You have a situation where you've got x squared here, you've got x squared here. This coefficient is a 1. So that means that this a plus b has to equal 1, because these coefficients, if these expressions are the same, then 1x squared should equal a plus b times x squared. So a plus b has to equal 1. 1x here, so c has to equal 1 by default, because c is the only coefficient of x. And 2a has to equal 3. So these are my equations here. This is the equation that she had this equation, but this is the next part where there was a mistake. So we're going to solve the system, which is the same system we had seen on previous page. And yes, I did this by hand. You can do this with a calculator. You don't have to show all this work. I just showed some of it to help you. I started with 2a is equal to 3. So I said, well, if 2a is equal to 3, then a is 3 over 2. C is 1. Now I could have just put in 3/2 and moved it, but I chose to actually solve this equation by eliminating the fraction. So I multiplied everything by 2 and I got 3 plus 2b equals 2. And I did the math and I got 2b. I subtracted 3 from both sides and I have 2b equals -1, b equals a -1/2. So now I've got my coefficients. A is 3 over 2. B is -1/2. C is 1. So now I go back to my partial fractions. Notice I haven't integrated yet. I'm getting ready to, but I'm setting up my partial fractions still. Here, A, what's A? A is 3 over 2. So 3 over 2 over x plus, I just used the default plus. You could just use a minus, but I didn't want it to be confusing to you. B is -1/2 x plus c plus 1 all over x squared plus 2. Now, then we're going to integrate this. So the integral of this fraction, dx, is equal to the integral of these two fractions that we created, dx. Okay? From here, it just gets to be a lot of algebra manipulation initially before we do some calculus. I mean, we've already done a lot of algebra, but we're going to do a little more algebraic manipulation before we do some calculus. So we have, this is 3/2 divided by x. So this is 3/2 times 1 over x dx, which is more useful to us in taking in antiderivatives. Here, what I did was I said, well, you know, the derivative here is going to be 2x. So I could do something with that, but what I'm going to do is I'm going to split this integral apart. So I said this is like saying -1/2 x over this denominator plus 1 over this denominator. Okay. And so I got there, but not just yet. So first I wrote it as -1/2 x times x squared plus 2, and then plus 1 over x squared plus 2 dx. So I now have 3 integrals to evaluate. Okay. Now I tried to show you, and I'm going to show you more on the next page, more details. Each of these integrals requires either a separate formula or a little different strategy. This 1 over x dx, we learned at the tail end of Calc 1 or the beginning of Calc 2 when we were doing the review worksheets, depending on when you were exposed to it. But this should be an integral that you're familiar with. The integral of 1 over x dx is the natural log of the absolute value of x. So we have 3/2 times the natural log of the absolute value of x. Now the second integral requires a different strategy. It requires a u substitution. And this third integral, you might initially think, oh, I can just do the natural log, but I've got x squared down here, and I can't split this. Unlike this one, I can't split it because I only have one term down here. Notice when I split the other integral, the other fraction, I should say, when I wrote it as 2, I used the whole denominator and I used each addend in the numerator. So I used each part of what I was adding. Here I can't do that because I only have one thing at the top. So this is not going to work to split it like we did. This is actually inverse tangent pattern. So if you need help with that, go back to the inverse trig functions, not the trig substitutions, but the inverse trig functions that we practiced in, I believe that was review 5 that we did that. In any case, let me show you in some additional detail down here. So we have -3/2, 1 over x. This is pretty straightforward for most of you, I think. 3/2, natural log absolute value of x plus c. Here I showed you the u sub in more detail. So I pulled out the -1/2 because it was already there. And then I have to make a u substitution. I get another 1/2 from my x dx here. So this becomes -1/2. I put the 1/2 in, put the 1/2 in, and I get -1/4 because I already had a -1/2 before that. And then this just becomes 1 over u again. So it's the natural log, the absolute value of u. Remember, u was the quantity of x squared plus 2. So I have -1/4 absolute value of x squared plus 2 plus e. Now this integral, this third one, 1 over x squared plus 2 dx. I gave you the little pattern. Recall that the integral of 1 over x squared plus a squared dx is 1 over a times the tangent inverse, or the arctan, of x over a plus a constant. Well, 1 over x squared plus 2 implies that 2 is a squared, because that has to match our pattern. We have x squared, we have the plus, a squared is 2, so a is √2, and I wrote it like this. So this integral becomes 1 over √2 tangent inverse of x over √2 plus a constant. So those are your 3 integrals that you split apart. So if we come back here, these are the 3 integrals that we broke apart, okay? And we now have this integral that we started with is 3/2 the natural log absolute value of x minus 1/4 times the absolute value of x squared plus 2 plus 1 over radical 2 times the tangent inverse of x over rad 2 plus a constant. Okay. I hope that this walkthrough of this example and pointing out a couple of the pitfalls and a couple of the things that you asked about in class has helped you. And I will include the worked solution that I generated, the same work solution that you're looking at. I will include that with the message when this video goes out, so you can download it and refer back to it if you choose, okay? If you have any questions, please let me know. Enjoy your weekend, and I will see you soon in my next video. Bye for now, folks.